Hi guys, welcome to video lecture number 2, velocity. The word velocity is often used as if it means the same thing as speed. For example, sports commentators say things like, that pitcher has a velocity of 95 miles per hour. What they are really describing in a statement like that is the speed the pitcher is throwing the ball with, or how fast the ball is traveling. The word velocity actually has a very specific meaning. And although it is related to speed, there is a distinct difference. The simplest and most common definition that is thrown out there for velocity is simply speed with a direction. This is a great starting point for understanding velocity. When you say something is traveling at 5 meters per second due north, you have described its velocity because you have described its speed, how much distance it is traveling in a given amount of time, and the direction that it is going, how it is changing its position. We've already discussed how distance can be described in two different ways. In one sense, distance is just how far you go. In another sense, distance is the path between two positions. When you're talking about velocity, you are using the second understanding of the word distance. Distance as a change in your position. Velocity requires you to have a frame of reference or a point of reference, usually the position that the object starts its motion at, but always a position it is moving away from or headed towards. If you describe an object's motion by saying how fast it is moving, and where it is coming from, or where it is going, you're describing its velocity. That's why the equation for calculating velocity is a change in position divided by a change in time. This triangle is called delta, and it means change in math and in science. This equation is just like the equation for speed, but it reveals an object's direction of travel as well. Just like speed, velocity is a rate. The equation probably looks a lot like something else you've seen in your math classes, and from the last video, you've probably guessed that the slope of a line for velocity is going to tell a story about its motion. I think the best way that I can explain the difference between speed and velocity to you is to show you a data table and a graph that represent the speed of an object's motion, and then show you a data table and a graph that represent the exact same motion but with velocity. So I also promised you in the last lesson that I would show you how to calculate instantaneous speed. The equation for speed is distance divided by time. And if we wanted to calculate the average speed, we would take the total distance this object travels, 10 meters, and divide it by the total time that it traveled, 5 seconds. So for average speed, 10 meters divided by 5 seconds will give us a speed of 2 meters per second. Recall that this is just the average speed of the object. Finding the instantaneous speed is also relatively easy. We use the same equation, but we can choose any given point in time in the data table. So let's choose the 3rd second of its travel, when it goes from seconds 2 to 3. That is 1 second of travel, and during that second, it moves a total distance of 2 meters. So to calculate the instantaneous speed at that given point in time, we take the distance that it traveled in that 1 second, and we can say that the instantaneous speed, how fast it was traveling during second number 3, was also 2 meters per second. Okay, let's go ahead and graph this object's motion. At 0 seconds, we have 0 distance covered. At 1 second, we have gone 2 meters. At 2 seconds, we have gone 4 meters. 3 seconds, we've gone 6. 4 seconds, we've gone 8. I have that last data point off. You have to excuse me. Okay, it's a little bit off, but we can live with it. And at 5 seconds, we've gone a total distance of 10 meters. That gives us a nice, perfect sloped line where for every 2 meters that the object travels, it takes 1 second to get there. So the slope of our line is 2 meters per second, which happens to be the same as the instantaneous and average speeds that we calculated in the data table. I think you guys could recognize, even as I was graphing those points, that all these instantaneous speeds are the same as the average speed. This object is moving at a constant speed of 2 meters per second. Now, we've described the speed of this object. Let's take a look at its velocity. If we want to calculate the velocity of the object, I told you velocity is a change in position over a change in time. And recall that a change in position is just another way of describing a distance, but with direction included. Now, this is going to look a lot like the slope calculations that you do in your math classes. Position 2 minus position 1 over time 2 minus time 1 will give us a change in position over a change in time. And we can choose whichever positions from the data table that we want. But let's take a look at the first one. During the first second, we have a change in position of 2 meters. Now I did that kind of the shorthand way. If we use the full equation, we would say that position 2 is here and position 1 is here, and time 2 is here and time 1 is there. Remember, position 1 and time 1 will always be the smaller numerical values. So position 2 was 2 meters, position 1 was 0 meters, time 2 was 2 seconds, and time 1 was 0 seconds. And so we get a value of 2 meters over 1 second, a velocity of 2 meters per second. And you might say, how is that any different than the speed calculation we just did? When we graph this, that should become very apparent. Now, our numbers are not the same. Notice that our data tables are different, but I told you this velocity and speed graph and data table represent the exact same motion. How can this be? If you look at the data table, we could do the calculation, but I think you see it. In the second of travel, this object goes 2 more meters. It's going at a speed of 2 meters per second, or a velocity of 2 meters per second. But during the passage of time from the 3rd to the 4th second, something changes. We go from position 6 to position 4. Let's do that calculation real quick and see what we can see. So this is going to be position 2, and this is position 1, and this is time 2, time 1. Let's go ahead and plug it into our equation. Velocity equals position 2, which is 4, minus position 1, which is 6, the unit is meters, over time 2, which is 4, minus time 1, which is 3 seconds. So all of a sudden, we get a value of -2 meters per 1 second. -2 meters per 1 second. Does this bother you that we have -2 meters? If we converted this to a velocity, we would have -2 meters per second. This is weird because this is the same motion as in the speed graph. I think once we graph these values, the story that you see on the graph will make this number make more sense. What does that negative sign mean? So let's move away from the calculations and take a look at the graphs themselves. If we look at our data table, our first position is 0 and our first time is 0. And I'm going to hold off on moving these numbers on the y-axis for time. Let's just put them on the position axis. When we have gone 1 second, then we are at a position of 2. When we've gone 2 seconds, we're at a position of 4. When we've gone 3 seconds, we're at a position of 6. When we're at 4 seconds, something changes. We're back at a position of 4. And when we're at 5 seconds, we're back at a position of 2. The reason that I put all of these dots on the y-axis is to remind you that this motion is a straight line motion, just like the scooter lab that you did. But now let's go ahead and move these to the correct x-axis locations. So 0, 0 was our origin. At 1 second, we were at a position of 2 meters. At 1 second, position of 2 meters. At 2 seconds, we're at a position of 4 meters. At 3 seconds, we're at a position of 6 meters. At 4 seconds, we're back to a position of 4 meters. And at 5 seconds, we're back to a position of 2 meters. So instead of a nice straight line, we have this V shape. That negative velocity that may have bothered you, the calculation, the negative slope of the line on our graph represents a direction change. As time passed, this object went away from its reference point, the starting point, 0, and traveled at a constant speed for 6 meters, and then turned around and traveled back towards the reference point before it stopped its motion at a position of 2 meters. All of this motion happened on a two-dimensional number line. The graph comes out looking like a hill. The number one misconception that students have about velocity graphs is that in some way the object's motion went up and then down, when in reality the object's motion is away from its starting point and towards its starting point. It traveled away with a velocity of 2 meters per second, and then it turned around and traveled back with a velocity of negative 2 meters per second. Both graphs, even though they look different, represent the same motion. The object always traveled with a constant speed of 2 meters per second, but our position time graph that represents velocity shows a direction change in that object's motion. Thanks for watching.